Hello and welcome back. Today we're going to solve questions on Surds. But before we actually jump right in, let me try to give you an understanding of what Surds are and what kinds of numbers are they. So Surds are numbers of the form root 3, root 2, root 5, root 7. Basically, the square root of numbers that are not perfect squares. Okay, so for instance, if you had root 4, this will give 2, so this does not give a surd. Alright, but these are surds because if we evaluate any of these, it's going to give us what we call an irrational number. An irrational number is a number that, they usually look like this: 4, 5, 7, 9, 2, 3, 3, 5, 6, 8, 7, 4, 3, 1, and they just keep going. Never-ending numbers. They are irrational, and they are called irrational because you cannot form an exact ratio from this number. No, you can't do that, and that is what makes them irrational. Now, of course, other irrational numbers you might know is pi, which is 3.1415 something something something. It just keeps going, never ending. You can't get an exact ratio. Now, of course, the usual ratio used to represent pi is 22/7. This number is close to pi, but it's not equal to. It's not equal, all right? We usually use this as an approximation, actually, but it's not equal to pi. So you should remember that. Also, the Euler's number, which is 2.7 something 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 something, just also keeps going, is also an irrational number. So as you can see, they are irrational because we cannot get exact ratios out of them, not because they are crazy or something. All right? Okay. So now that we have that out of the way, let us do some addition of sets. Now, addition and subtraction of sets basically work like addition and subtraction of variables. So just like we know that when you have 2x plus 3x, since the variables here are the same, they are like terms, we can easily add the coefficients to get 2 plus 3, 5x. Similarly, if we had 2 root 2 plus 3 root 2, since the third part, the irrational part, is the same, then we say they are like terms, so we can add the coefficients to get 5 root 2. Alright, and also if you were to have 3x plus 2y, you wouldn't be able to add these because their terms are different. So these are different terms, so this will give you the same exact thing, non-changing. So in the same way, if we have 3 root 3 plus 2 root 5, these irrational parts are different, so we will not be able to add the coefficients in this situation. So this gives you the same exact thing. Alright, subtractions also work similarly. So if we were to have 2 root 2 minus 3 root 2, since they are like terms, we can subtract the coefficients to get 2 minus 3 minus 1 root 2. Now whenever there's 1 before the surd, before the irrational number, we just not write the 1, just leave it as such. So this gives minus root 2. Okay, and also if you had 3 root 3 minus 2 root 2 plus 2 root 3 minus 5 root 2. So you find that some of the sets are the same. I mean, there are like terms within this expression. So what we first do is group them. So we want to put root 3 on one side and root 2 on the other side. So we have root 3 plus 2 root 3. And remember that when grouping, each number comes with their sign, whether they are positive or negative. And of course, if you don't see any sign before a number, that's positive. Minus 2 root 2 and minus 5 root 2. Now we can evaluate this. So 3 root 3 plus 2 root 3. Since these are the same, we add the coefficients to get 5 root 3. Now minus 2 root 2 minus 5 root 2. The roots, the third part is the same again. So minus 2 minus 5 is minus 7 root 2. And we will not be able to do anything further because the resulting expression here has different terms. So we leave it like this. So our answer will be 5 root 3 minus 7 root 3. Oops, sorry. I'm trying to clean this. Okay, now that we understand how addition and subtraction of surds work, let's move on trying to simplify some expressions in surd form. So for instance, if you were given root 27, you were asked to simplify. Now, root 27, now of course, we know 27 isn't also a perfect root. However, its multiple, it has a multiple that is. So whenever you are given expressions such as this or this, basically the root of a fairly big number, which you know has a multiple that is a perfect root, or this, and so on and so forth. Yeah, the first thing you want to do is change the number within the root into the multiples containing the multiple that is a perfect root. All right, so for instance, for root 27, you know that this is the same as the root of 9 times 3. Now 9 times 3 gives 27. Now we didn't just do this for fun. Whenever you have multiplication within a surd like this, you can actually change it to root 9 times root 3. So you have to remember, let me put this as a rule here. Square root of a times b is equal to root a times root b, and vice versa. So that is root a times root b is equal to square root of a times b. Very important to remember. So once we have this, now we know that this is a perfect square. So we resolve that. So what we'll have will be 3 times root 3. And since we can't do anything further, we just multiply them. And of course, you can multiply these to get 3 root 3. And this is the final answer. So this number, root 27, is the same as 3 root 3. Is that okay? All right. So you can try to resolve, you can try to simplify root 32 and see. You can pause the video and try to simplify. Otherwise, I'm just going to go right in. We know that root 32 is the same as 16 times 2. 16 times 2 gives 32. And by the way, since you are allowed to use calculators in your exam, whenever you are given numbers like this, first divide them into small numbers like 2, 3, 4, and 5, and so on, to see if you get a perfect square. Yeah, to see if you get a perfect square. If you do, then that becomes your what you use to do the multiplication. So in this situation with 32, if we divide by 2, we get 16. So we can say 16 times 2 because we divided by 2 here, and so on. And also with 27 here, 27 divided by 3 gave 9. So we see that there's a perfect square. So we had 9 times 3 within the square root, and then we simplified it. So that's the neat little trick you can use. Okay. So here we have root 32 is equal to root 16 times 2. Now 16 is a perfect square again, but then we first break them out. So this gives root 16 times root 2. Now root 16 is 4, so this gives 4 times root 2, and this is equal to 4 root 2. So root 32 is the same as 4 root 2. Alright? Let's do a couple more. Now we have root 8. Root 8. Again, we divide by 2, and then we find that there's 4 times 2, and 4 is a perfect square. So that's what we use. So we have root 4 times 2 gives root 4 times root 2. And root 4 gives 2. So we have 2 times root 2, and this is equal to 2 root 2. Okay. And now root 1 to 8. So again, like I said, you divide by one of those small numbers. So 1 to 8 divided by 2 gives 64. And 64 is a perfect square. So we have root 128 is equal to root 64 times 2. Okay, and this gives root 64 times root 2. And this gives us root 64 is 8 times root 2. And this gives 8 root 2. And this is how to basically simplify surds. Now why don't we combine simplification with our addition and subtractions and try to make this a little more complex. And as I write down the expressions to be simplified, you can pause the video and try your hands on it to see if you can do it, applying what we've learned so far. So let's say we are to simplify root 1 to 8 minus root of 50 plus 2 over 3 root of 162. Okay, so you can pause the video and try to see if you can actually solve this. Otherwise, I'm just going to jump right in to do it. Okay, so now first of all, the first thing you do, since you have numbers within there that have multiples that are perfect squares, you simplify the individual surds first. Alright, and actually that's the only thing you can do. So you do that hoping that you will get some like terms here, so you can add or subtract. So first we simplify the surds. So root 1 to 8, we know from before, is 64 times 2, root of 64 times 2, and this gives root 64 times root 2, and this gives 8 root 2. Root 50 is equal to the square root of 25 times 2. 25 times 2 gives 50, and we can and so we can break this up to root 25 times root 2. Root 25 is 5, so we have 5 root 2. And root 162, again, if you divide this by 2, you'll get 81. And 81 is a perfect square. So we have root 81 times 2. And this gives root 9 times, sorry. And this gives root 81 times root 2. And this root 81 is 9 root 2. So all these terms, we have simplified them to this. and you see some neat little thing here. Everything is in root 2, so meaning we can add them easily. So in place of these, we actually write out all these. So this is given by root 8 root 2 minus, in place of root 50 was equal to 5 root 2 plus 2 over 3 root 162 is 9 root 2. Okay, now we can see that over here we have 2 over 3 times 9 here, so we can do a little simplification. 3 times 3 gives 9, so 9 divided by 3 gives 3, and so this evaluates to 6, and then we can do some addition. Let me just do it on top here. So we have 8 root 2 minus 5 root 2 plus 2 times 3 gives 6 root 2. Now since again they have the same terms, we can add the coefficients. 8 minus 5 is 3 plus 6 is 9, so all this gives 9 root 2. Okay, I hope this was a good exercise of combining addition, subtraction, and simplification. Okay, let's try some more. Let's try some more. Let me just clear the entire screen. Okay, so we have to simplify root 500. You can pause it and try. Otherwise, I'm just going to go right in. This is the same as root of, 100 times 5 gives 500. 100 times 5, and 100 is a perfect square. So this gives root 100 times root 5, which is equal to 10 root 5. Also, root 72. Root 72 is equal to root of, now 72, again, do a little division. If you divide, you see it gives 36, and 36 is a perfect square. So 36 times 2, which is equal to root 36 times root 2, and this gives 6 root 2. Okay, and we can go on and on and on. Let me just do the last one here. Root 450. Root 450. Now sometimes it can be, let's see, 450. So again, you can divide by 5. I think if you divide by 5, you get like 90. 90 is not a perfect square. You can then divide by, I think 2. You get 2, 2, 5. Yes, and this is a perfect square. So again, you use your calculator to play around with it. So you have 225 times 2. And this gives root 225 times root 2. Root 225 is 15. So this gives 15 root 2. Okay? Alright. So let's move on to some more. Allow me to introduce you to rationalization of denominators. So let me clear the screen. Now, whenever you have a surd in the form 4 divided by root 5, so anytime you have an expression with the surd, the irrational part, as the denominator, what you should do and what you are required to do is to eliminate it from there. Basically remove it from the denominator. We need it to be up here, not here, in order to do computations easily. Alright, and the technique of bringing it, the technique of removing the irrational number from the denominator is called rationalization. Rationalizing the denominator. So rationalizing the irrational number means we basically convert this into a rational number. That's all it is. So how do we rationalize this, for instance? Now remember that whenever you have a fraction, say 2 divided by 3, if I multiply it by 1, it gives the same exact thing. Anything times 1 is that same number, right? So remember that this is the same as, when you have 1 here, it's the same as 1 over 1. This is the same exact thing, right? And this is the same as 2 divided by 3 times 1,000 over 1,000. Remember, this 1,000 divided by 1,000 is 1. So this gives the same exact thing, right? So is this technique we're actually going to use to rationalize the denominators. How is that? So this is how we do it. Let me just rewrite it down here. 4 divided by root 5. In order to rationalize it, we want to multiply it by 1. But what about multiplying by root 5 divided by root 5? Now a number divided by itself is always 1. So we didn't do anything to this. This will come out to be the same fraction. But then this allows us to do some multiplications, which will help us remove the rational number from the denominator. Alright, and that basically is rationalization. So you realize that we can multiply the numerators and the denominators. Alright, so 4 times root 5 gives 4 root 5. Root 5 times root 5. Root 5 times root 5. Now whenever you have this, it's the same as 4 root 5 divided by 5. Yes, you should know that the root of any number times itself is equal to that number. Very important. Alright? Because actually you can see that root 5 times root 5 is equal to the big root 5 times 5, which is equal to root of 25. 25 is a perfect square, and this gives 5. So in the same way, root a times root a is equal to root of a times a. And since a times a, that's a perfect square, this basically gives a. Right? Just root a, which is equal to a. So this is something you should remember for rationalization. And this is how it's done. So as you can see, we multiply the fraction by the surd. We multiply the fraction by the irrational number divided by itself, and then we multiply it out, and in that way we'll be able to rationalize the denominator and then get our final answer in this form. Let us do a couple more examples. Let me just clear the screen. So we have so this is express 1 plus, and you meet a question like this 2 in the form p plus q root 2. Now you shouldn't let these expressions scare you. Once you have a surd that clearly needs simplification, that is what you should do. You simplify it, and then you know later on see if you can express it in this form, and that's all it is. Now we can clearly see that this expression needs rationalization. We can't leave the root 2 in the denominator as such. So 1 plus root 2 divided by 2, root 2. We multiplied the numerator and the denominator by the rational number in the denominator. Now again, this gives 1, so we didn't really do anything to that fraction, but it allows us to do multiplication. So this gives root 2 times 1 plus root 2. That's root 2 times all of these divided by root 2 times root 2. We can expand this, so we get root 2 times 1 gives root 2 plus root 2 times root 2 gives 2, right? Divided by root 2 times root 2 also gives 2. So now we can actually try to express this in this form. So how do we go about that? So we break these up into individual fractions. So this gives root 2 divided by 2 plus 2 root 2. This can be broken up into that. Okay, because there's a plus here and they all have a common denominator, you can actually separate them into this form. And remember, just to show you, you find the LCM 2, and then you will see that this gives 2 plus 2, the same exact thing. So that's just what we're doing. So once you do this, you'll realize this cancels out to give 1, and so you have root 2 divided by 2 plus 1. Now we can rearrange it so that the rational part is on the right hand side so that it looks like p plus q. So this gives 1 plus 1 over 2 root 2. Now you see, instead of root 2 over 2, I split it up to get half root 2. If you multiply this, you get root 2 over 2. But I only did this so that it looks like the expression given p plus q root 2. So from here I can see that p is equal to 1 and q is equal to half. And this is how our final answer will look like. Alright, so you basically simplify. Sometimes you might need to simplify this side itself and then rationalize the denominator like we did, and then you now try to express it to look like the expression given, and then you basically match them. So p is like 1, q is like this, and so that's our final answer. Okay, let's do a little more. So let's solve. Let's simplify 1 over root 2 plus 1 over 3 root 2. By the way, this 3 should be bigger, else it'll look like cube roots, which isn't what I'm looking for. So again, we rationalize each of these fractions. Alright, so this gives 1 over root 2, rationalizing this times root 2 over root 2. So that is this, plus the other fraction times 3 root 2 over 3 root 2. Okay, and so doing this, we get root 2 divided by root 2 times root 2 plus 1 times 3 root 2 gives 3 root 2 divided by, now when multiplying these, watch out, you multiply the coefficients differently. So 3 times 3 gives 9, and then you now multiply the surd part separately. Root 2 times 2. Okay, and so we can evaluate root 2 times root 2 gives 2 plus 3 root 2 divided by, this also gives 2, 9 times 2, and this whole entire expression gives root 2 over 2 plus 3 root 2 over 18. Now of course we can do a little simplification here. 3 18 is divisible by 3, right? 6 times. So this further simplifies to root 2 over 2 plus root 2 over 6. And guess what? They are like terms, so we can actually add them, right? Let me create some space. I think I'm writing a little too big. I hope you can bear with me. So what I'm trying to do is root 2 divided by 2 plus root 2 divided by 6. Since the surd parts are the same, we can actually add these. So we can use LCM, is 6. So 2 into 6 is 3 times. 3 times root 2 gives 3 root 2 plus 6 goes here 1. 1 times root 2 is root 2. And so we can clearly see that this can be added to this. Remember I said there's 1 here. So 3 plus 1 is 4. We have 4 root 2 divided by 6. And of course again we can divide these. And this gives 2 root 2 divided by 3. Or 2 over 3 root 2. However you need the answer. And that's the final answer. So that's rationalization and combining with multiplication and combining it with addition and subtraction. Let's do a couple more, right? I'm erasing the whole thing. I'm going to try to be a little more economical about my space. So again, we have to express 1 over root 5 plus root 3 in the form p root 5 plus q root 3, where p and q are rational numbers. So this is the challenge today. Okay. Now, remember I told you that if you have a fraction like this, for instance, to rationalize it, you multiply it by the top and the bottom by the surd, just like that. And of course, that gives root 5 divided by 5. And that is how you rationalize it when there's a single surd expression down there. However, when you have a more complex expression, such as we have here, you do it a little different. So 1 divided by root 5 plus root 3. Again, we multiply the numerator and denominator by some things. But what do we multiply it by? Now here's it. We multiply by root 5 minus root 3 divided by root 5 minus root 3. Now first of all, again, you can see that these, the top and down, are the same. So they cancel out to give 1. So we are basically multiplying 1 by this, which gives the same thing. So it doesn't really change it. But then, why did we change the sign from positive to negative? This is known as the conjugate of that. So just before we solve it, let me show you a little bit. So whenever you have a surd in an expression, so for instance 2 plus root 3 or root 2 plus root 5 and so on and so forth, the conjugate is basically changing the sign. Root 2 minus root 5 and so on. This is called conjugate. Why is it called a conjugate? Because if we were to multiply these and this and that, well, let's see what we get if we multiply them. So let's say we have 2 plus root 3 times 2 minus root 3. Alright, so we expand by foiling. 2 times 2 gives 4. 2 times minus root 2, so we have 2 minus 2 root 3. Root 3, sorry. Root 3 times 2 gives plus 2 root 3. And this gives minus Root 3 times root 3 gives 3. Now you realize that this cancels out, so that 4 minus 3 is equal to 1. And that is how you rationalize expressions like that. If you multiply it by the conjugate, the resulting answer must give you a rational number, right? Because in the end, within the expansion, the irrational part will actually cancel out, so that you are left with rational numbers, and then you can just solve to get your answer. So that is why we multiply by the conjugate of the surd expression, the surd or surd or said, however it is you pronounce it. Okay, so let's go ahead and solve our little question. So multiplying these out, of course the numerator remains the same, root 5 minus root 3, and the denominator is root 5 plus root 3 times root 5 minus root 3. Alright, so expanding this gives root 5 minus root 3 divided by root 5 times root 5 gives 5. Remember, the same roots, so it just gives 5. Root 5 times minus root 3, so we have minus root 5 times root 3. Okay, let me just write it out this way first. Man, this is usually too big, isn't it? Root 5, root 3. Now, root 3 times root 5 gives plus, and it's positive here. Root 5, root 3. And plus root 3 times minus root 3 gives minus 3. Root 3 times 3, root 3 gives 3. So as we can see, this part cancels out, and so we are left with the numerator remains the same, divided by 5 minus 3, and this gives root 5 minus root 3, all divided by 2. So now that we have this, now we try to express it in the form they have given. So they said it must look like p plus root 5 plus q root 3. So meaning root 5 must be the first term, and then root 3 will be the second term. So we basically break this into two separate fractions. Again, this is equal to root 5 divided by 2 minus root 3 divided by 2. Now straight away we see that this is equal to half root 5 minus half root 3. So from this, p is equal to half, and q is equal to minus half. Remember, minus half. Remember, the expression gave plus, and ours gave minus. This means that q, the value of q must have been minus something, which is this. Alright? And that is our final answer. So this expression is of the form this. Anyway, if you have any questions and comments, you can leave them below. Don't forget to do that. Okay, so let us try to solve a bit more. So just something on conjugates. I think this particular question, sorry, okay, not exactly. We have to expand this to root 2. Now you can pause the video and try to expand it, otherwise I'm just going to go refoil. So 1 times 3 gives 3. 1 times 2 root 2, which is positive, gives 2 root 2. Now minus root 2 times 3 gives minus 3 root 2. And minus root 2 times positive 2 root 2 gives minus 2 root 2 times root 2. Alright, and this gives 2. So this is equal to 3 plus 2 root 2 minus 3 root 2 minus 2 times 2, which is 4. 4. 2 root 2 minus 3 root 2. Remember, the irrational part is the same, so we can subtract the coefficients. So we get 3. Now we gather like terms as we do that. So minus 4, we bring minus 4 this way. Minus 4. 2 root 2 minus 3 root 2. 2 minus 3 is minus 1. But we don't actually write the 1, we just say minus root 2. And so 3 minus 4 is minus 1. So minus 1 minus root 2. And this is the expanded form of that. Alright. Alright, let's solve this. 20 minus root 45. So again, you resolve these into multiples containing at least one perfect square. Alright? Okay. So we find that, let's see, root 80 is equal to, I think, we have 40 times 2. Now, but 40 times 2 isn't exactly a perfect square now, is it? But that can further be broken down. So you see that you can actually do the multiplication multiple times. So 40 can further be broken down into 4 times 10. Yeah, it can. Right, so we say 4 times 10 times 2. So this is equal to root 4 times root 10 times root 2. This is a perfect square. So this gives 2. And root 10, we can't do anything about it. And neither can we do anything to that. So we multiply them out. So root 10 times root 2 is equal to 10 times 2, like so. And this gives 2 root 20. But within root 20, we can get another perfect square, can't we? So we further break that down. So this can go on and on. So this is beneficial if you were not able to tell the perfect square from the multiples at first glance. So 20 can be resolved into 4 times 5 and 4 here. So this gives 2 times root 4 times root 5. 4 here is a perfect square. So this gives 2 times 2 times root 5. And this is 4 root 5. And that's the final answer. No, not the final answer, but that is the simplification of root 80. It gives 4 root 5. Okay. So we have root 80 is 4 root 5. Now we do same for root 20. Root 20 is quite straightforward now, isn't it? So root 20 is equal to root of 4 times 5. And this is equal to root 4 times root 5. 4 is a perfect square, so we have 2 root 5. So we have 2 root 5 up here. And now we have root 45. Root 45 is equal to the root of 9 times 5. And this gives root 9 times root 5. Root 9 is a perfect, can give us a perfect irrational number. So this gives 3 root 5. And so this part is 3 root 5. So with this, we can rewrite the whole entire expression. can rewrite the whole entire expression to get 4 root 5 plus 2 root 5 minus 3 root 5. And of course, the irrational part is the same throughout, so we can do the math. So 4 plus 2 is 6, minus 3, 3. So we have 3 root 5. And this is the final answer. Okay. So a couple more. Now let's just, so you can try your hand on this before we move on to more complex ones. So again, we simplify each of them separately. So 3 root 8 can be 3 roots. 8 can be resolved into 4 times 2, which is equal to 3 root 4 root 2. This is perfect, so this gives 3 times 2 root 2, which is equal to 6 root 2. And root 50 is also equal to root 25 times 2, which is equal to root 25 times root 2, and this is equal to 5 root 2. And so we can now replace them here and solve our, and really simplify the expression. So we have 6 root 2 plus 5 root 2. Again, the irrational part is the same. We treat them like a variable, like I said. So this gives 11 root 2. And that's the final answer. Okay. Now let us do more of the rationalization with a complex denominator. With complex denominators. Okay. So we have express 4 root 3 plus 3 root 2 divided by 2 root 3 plus 3 root 2 in the form p plus q roots r. So with this, now of course p plus q root r, so that means you basically express it in this form. So again, once you look at this expression, you can tell that it needs rationalization, and that's exactly what we're going to do. 4 root 3 plus 3 root 2 divided by 2 root 3 plus 3 root 2 times, so we multiply the top and the bottom by the conjugate of that, which means we change this. So we have 2 root 3 minus 3 root 2 divided by 2 root 3 minus 3 root 2. So then we do that. So we are multiplying these. So I'm just going to multiply them straight away for want of space. So I fold this over that. So 4 root 3 times 2 root 3. So 4 times 2 is 6. Root 3 times root 3 is 3. So this gives 6 times 3. Now this times the second one. So 4 times 3. And this is minus, so I bring the minus. 4 times 3 gives 12. And root 3 times root 2 gives root 6. So this gives root 6. Remember, root 3 times root 2 is the same as root 3 times 2, which is equal to root 6. You should do this so much that you become very good at it, because there are more complex things coming up. Alright, so we have finished foiling this over that. We now take this and foil it over that. So 3 root 2 times 2 root 3, and it's positive. They are both positive, so plus 3 root 2 times this. So we multiply the coefficients first. We have 6 times root 2 times root 3 gives root 6. And again, this times that gives minus 3 times 3 gives 9. And root 2 times root 2 gives 2. So that is the top. And that divided by the bottom. Alright? So again, this times that gives 2 times 2, 4. Root 3 times root 3 gives root sorry, it gives 3 times 3. Now this times that, just minus 2 times 2 3 times 3 root 2. So 2 times 3 gives 6 times root 3 times root 2 gives root 6. Now 3 root 2 times this. So we have plus 3 times 2 is 6 root 6. And this times that gives minus 9 root 2. Okay, so now that we've done this we can see that 6 root 2 cancels 6 root 2, and so we are left with, and we basically evaluate these two. This is 12 root 6 and this is 6 root 6, and since they are the same here, this minus 12 plus 6, so this is like 6 minus 12, so this gives minus 6 root 2. So 6 times 3 is 18 minus 6 root 2 and minus, sorry, 6 root 6, and then minus 9 root 2, all divided by 4 times 3 gives 12 minus 9 root. Sorry, there was a mistake here. When multiplying this by this, root 2 times root 2 gives 2 actually. So this is not root 2. And this is how you can actually check your rationalization. After rationalizing, you must not have a surd in here. So this must give 9 times 2, which is 18. So we have to have 18 here instead. So minus 18. So this gives 18 minus 6 root 6 minus 9 root 2 divided by 12 minus 18 gives minus 6. Now we go back to see what we are expressing it in. We are expressing it in the form p plus q root 3. Alright? So we basically break up these into individual fractions. Since they have one expression, one number as a denominator, we can break them up. So this will be equal to 18 divided by minus 6. So this makes this whole thing minus. Minus. You know what? Just so that you don't get confused with the negatives, you can multiply the top and bottom with minus 1 each, so that we can take away this negative sign from the denominator. Alright, so when that happens, things will be rearranged here. All the positives will become negatives and all the negatives will become positives. So we are going to have, so I'm just going to rewrite them. Since this becomes, oops, didn't change this. Since this becomes positive, we write it first. So this gives 9 root 2. This also becomes positive, plus 6 root 6. And this becomes negative minus 18, all divided by 6. So now we can have 9 root 2 divided by 6, plus 6 root 6 divided by 6, minus 18 divided by 6. Now 3 in 6 gives 2, and 3 here gives 3. 6 cancels 6 up here, and 6 can go into 18 perfectly to give 3. Alright, so I'm just going to write this part here. I hope this one can convenience you very much. You can manipulate the video anyway. You can pause forward and then see what I'm claiming here right now. So 3 divided by 2 root 2 plus root 6 minus 3. So this is what we have. Now they want us to express it in the form this, meaning the root part must be second, as in it must occur here. Right. So the rational number will basically stand alone. So meaning we have to bring this first. So this is equal to minus 3 plus root 6 plus 3, sorry, 3 divided by 2 root 2 plus root 6. Alright. Okay. So this basically expresses the expression in that particular form, where minus 3 is p, but this whole entire expression is actually q root 3. So q root 3 basically means the expression with the irrational number, and this whole expression has the irrational number. So this does the trick. So let us move on. Let us do a couple more of these. So we have to simplify. 1 divided by 3 root 7 minus 5 minus 1 divided by 3 root 7 plus 5. So to do this well, you can decide to rationalize them first, or you can find the LCM, which basically does the rationalization in a way. Alright? Okay, so let's do the LCM part. So again, like I said, you can just rationalize these. So 3 root 7 plus 5 over 3 root 7 plus 5, and then this is plus, so this will be minus. You can do this. You can try it out and then compare it to what we are going to get now. So we are trying to find the LCM of this. So we basically multiply the two together. So we have 3 root 7 minus 5. And it's best to not expand them straight away for good reason. So now this goes into this times. So this times 1 gives 3 root 7 plus 5 minus this goes into this times. So this times that gives 3 root 7 minus 5. So now we see that when we multiply these out, we are going to get a rational number at the bottom here. So this gives 3 root 7 plus 5 minus 3 root 7 minus 5. And weirdly enough, you can see that this actually cancels out. Let's see. 5 minus 5 is 0. 3 root 7 minus 3 root 7 is 0. So this whole expression actually gives you 0. So since the numerator is 0, it makes everything 0. Alright? You can just try to expand this to see. So we have 63 plus 15 root 7 minus 15 root 7 minus 25. So, and again, sorry, let me just, such a mess. So the top gives 0. 63 minus 25 gives you 63, 38, and this is equal to 0. Now let us try to rationalize the top and the bottom first. See what we have. So that expression should basically give you 0. Okay. So rationalizing, we have 1 divided by 3 root 7 minus 5 times 3 root 7 plus 5 divided by 3 root 7 plus 5. So let's just first rationalize this. This gives 3 root 7 plus 5 divided by, so well, we did that to get 38, right? You know, you expand this by 4 in it, you get 38 here. And now rationalizing the other part, 1 divided by 3 root 7 plus 5 gives 3 root 7 minus 5, 3 root 7 minus 5. And this gives 3 root 7 minus 5 divided by 38 also. So 3 root 7 minus 5 divided by 38, no, plus 5 here, minus 3 root 7 minus 5 divided by 38. These are like the same exact expression. The LCM will be 38 since it's the same, so the two numbers will just come together just like that. Minus 3 root 7 minus 5. Again, you can see that 5 minus 5 gives 0, so this cancels out, and that also cancels out, and the top here gives 0. So again, you have 0 over 38, which is 0. So this expression simplifies to 0. Okay. So you can try more examples, and then yeah. So now let us solve this particular question. So it says if root 2 is equal to 1.4142, find 2 3 decimal places. 1, 3 divided by root 2 over 1, and 2, 3 root 2 minus 4 divided by 3 minus root 2. Now, when you see this, it is tempting to just substitute root 2 for this. But please, you must first rationalize. You simplify the expression until you can't do anything further before you substitute. You must remember that. So the first one says 3 divided by root 2 minus 1. You rationalize. So root 2 plus 1, and the bottom root 2 plus 1. And this gives 3 root 2 plus 3 divided by root 2 times root 2 gives 2 plus root 2 minus root 2 minus 1. So this gives 3 root 2 plus 3 divided by, this cancels out, 2 minus 1 gives 1, so which is just this. Now we can just substitute root 2 for 1.4142. So this gives 3 times 1.4142 plus 3. And so you can use your calculator. 3 times 1.4142 plus 3 gives 7.242 to 3 decimal places. Remember, so the number after the decimal point must be 3. So we leave it this way, and that's our answer. So when given questions like this, where you have to substitute a surd value, you simplify it until you can't do anything further, like this, and then you substitute the value given, and that gives you your answer. So, okay. Now I'm going to end the video with this and then come back to in the next video to do more complex surds and also surd irrational equations and solve more examples. So leave your questions and comments below. Don't forget to subscribe if you haven't already. Otherwise, till next time.